In this video, we'll look at some of the key ideas to help you to focus your attention in this short lesson in organic chemistry. There are two key skills that you need to have by the end of this. The first is that you want to be able to identify what are called families and functional groups within organic molecules, and you want to be able to use an IR spectrum to identify those functional groups. Keeping these two things in mind will help to narrow your focus as we're doing this very basic introduction to organic chemistry. So far, most of your studies in chemistry have been about inorganic chemistry. So when we're looking at sodium chloride and lead iodide and all of these ionic compounds and things like CO2 and H2O, those are part of what we call inorganic chemistry. When we're studying carbon-containing compounds, these are organic molecules. And organic molecules, the main atom is carbon, and their carbon atoms come in chains and rings, and it's the unique bonding in carbon that allows for millions and millions and millions of molecules to be possible. And we used to think of organic as being something that was found in nature, but the reality is we can actually synthesize organic molecules in a lab, so they're not necessarily things that are found in nature. They're often things that we create in a lab, mimicking things that are found in nature that are carbon-based. So there's tons and tons of organic molecules, and the classes of compounds that we have of them are called families. And here is a list of the families, and these molecules are grouped into these families based on their chemical and physical properties. So we'll see that they have what are called a functional group, and a functional group is the reactive center of a molecule. It often is what leads to the chemical reactions that the molecules will undergo, but also when we study bonding and properties, you'll see that they are central in deciding some of the forces that hold these molecules together and lead to their properties like their solubility and their boiling point and their melting point. They're all going to be connected to this functional group. So in this very basic introduction, our goal is just to be able to identify some of these different functional groups and be able to classify them based on what we see in the molecules. One of the things that's helpful to look at before we go too far into organic chemistry is to look at how the structures are made. And when we draw Lewis structures that are inorganic, like PO43- and SO42- and NO2-, we follow these steps for drawing the Lewis structures. And it's because sometimes in inorganic molecules and ions, the atoms will bond in multiple ways. So nitrogen might produce 4 bonds in one case, but in another case it might have a lone pair and 3 bonds. So we leave that strategy for inorganic molecules and ions. When we're studying organic chemistry, the atoms tend to bond based on what we would refer to as their bonding capacity. So we simply need to think about the number of valence electrons that the atoms have, and then we think about what's the expected number of bonds that we will see, and in organic chemistry they tend to follow that. So what I have here is a list of very typical atoms found in organic molecules, so we'll look through them one at a time. So one of the key ones is carbon. Carbon has 4 valence electrons, and so then we look, looking for an octet, that means that we would typically form 4 bonds in carbon. So when we're looking at organic molecules, we are always going to be making sure that carbon has 4 bonds. Hydrogen has 1 valence electron, and to fill up that first shell with 2 electrons, it will only need to form 1 bond. Oxygen has 6 valence electrons, and so what we'll see is that it will form 2 bonds, and you'll also notice that oxygen will tend to have 2 valence electrons. Two pairs of lone pairs of electrons. With nitrogen, it's got 5 valence electrons, and so it will typically have 3 bonds and 1 lone pair. And then sulfur, much like oxygen, has 6, so it will also tend to form 2 bonds. X we refer to as halogens, so those are chlorine or bromine or iodine, and they show up a lot of the times in organic molecules. They have 7 valence electrons and will have therefore 1 bond and have the 3 lone pairs. The other thing that is unique to organic chemistry is that we have multiple ways of representing our compounds. And so it's worth discussing, first of all, that when we look at formulas, we want to remind ourselves that we have both empirical and molecular formulas. And empirical formulas give us the lowest ratio of the atoms in the compound, while in a molecular formula, it gives us the exact number of atoms in a compound. And a molecular formula is what we would use to actually build the organic molecule. So in this example here of C6H14, that is how many atoms will be in this molecule of hexane that we're going to be looking at, this isomer of hexane. This is the simplest ratio, but on its own, it doesn't actually give us the total number of atoms. So while it's useful because we can determine it experimentally, it's not useful in terms of actually being able to build a structure. Now, the reason that in organic chemistry the molecular formula is not enough is, you can see even just in my discussion, I referred to this as hexane, and that would be one isomer of this molecule. So when we have organic molecules, there are many, many ways that a group of atoms can be joined together to build an organic molecule. And so molecules that have the same formula but a different structure, we call them isomers. And so what this leads to is the need to have a more descriptive formula or way of representing the molecule so that people know which isomer I'm referring to. So I'll look at this one first, the structural diagram. So when we look at this structural diagram, we can see here that it's showing us the way that the carbon atoms are organized in this molecule. So this is saying that we have 5 carbons in a chain, and then we have the hydrogens are attached to the carbon. You'll notice that each carbon has 4 bonds, each hydrogen has 1 bond in this molecule. And this has 5 in a row, so we call it a pentane, which is extra information you don't need, but just so that you know where the name is coming from. And then this group attached here, we're calling that the methyl group. Okay? So this is one way to represent a molecule. It's a typical Lewis structure where you're showing the atoms and how they're bonded. We can also represent it in this more simple way where we don't actually show the hydrogens. In organic molecules, we think of the hydrogens as being fillers in the molecule. We just have enough hydrogens. And so when we look at the backbone or the general structure, we just fill in the appropriate number of hydrogens. So for example, with this one, I would have said, okay, I have pentane, so I've got 5, and I know from the name that they're all single bonded. And then I've got this methyl group coming off of my second carbon. You'll notice it doesn't matter if I put it above or below. And then you can see that's the basic structure. And then because carbon needs 4 bonds, I can fill in the appropriate number of hydrogens. And when I tally it up, I'll see that I would have used 14 hydrogens, which is what is required for the formula. Okay, so that is a structural diagram. So you're not going to have to draw these at this stage. At this stage, you just need to be able to look at a molecule and understand that it's an organic molecule based on the fact that there's carbon in it, and be comfortable with the fact that carbon is always making 4 bonds and hydrogen is making 1. Okay, so like I said, we want to stay focused on what we need, okay, for this really basic introduction. Okay. This is actually a really typical way to represent molecules. They're called line diagrams, and these are the simplest way. And when you look up, if you were to look up vanillin or aspirin or some kind of known organic molecule online, and you looked at an image, you would typically see it represented in a line diagram. And with these, they're simplified because they're basically just showing the carbon backbone. So you can see at each point here, at each point, there is a carbon atom, and then the hydrogens are assumed. So you can see that it's the same backbone that I drew before, where I've got 5 carbons in a row, and then I've got one branch with a carbon coming off of it. Now with this, the hydrogens are assumed, and you can also see that it's taking on this zigzag nature. When we explore 3D molecules, you'll be able to see why it needs to be zigzag, but this is actually a better kind of representation of the actual shape that the molecule takes on. Okay. Another form, which we won't go over in detail right now, but another way that we can write a formula is through what's called an expanded structural formula. And so the way that this is written here is telling me how to draw the molecule. So it's saying CH3, and then you have a CH, and then this is in brackets, so it's telling me to make this come off as a CH3, and then I have CH2 2 times, and then I have CH3. Okay, so again, this is just showing you so that you can be a little bit more familiar with some of the different formulas that you might see. Okay. Now we're getting closer to what you want to be able to look at or identify at this stage in your studies, and that's to be able to recognize that we have these different functional groups and there are families associated with them. So when we look here at this table, we've got them all summarized. Okay, so with an alkane, okay, this is a very typical alkane, and there are all single bonds in alkanes. Okay, it leads to their properties, and they're both chemical and physical. Alkenes, you can see they have this double bond. So I won't do them for all of them, but for this one, I will draw this out. So you've got you've got 3 C's, and we've got a double bond between those 2 C's. And then to finish this molecule, I would put enough H's to make it so that every carbon had 4 bonds. Okay, so that's kind of the basic idea. So you could, if you want to, for practice, go through each of these and make the structural diagram from the line diagram. In some of the activities you're doing throughout this lesson, you will be doing stuff like that. Okay, so an alkyne has a triple bond. Benzene has this unique structure where you have a 6-membered ring with alternating double and single bonds. Alcohols have this OH group, okay, called a hydroxyl. Aldehydes and ketones are related to each other because they both have a carbonyl group, which is a C double bonded to O. The difference is the location of the carbonyl group. So in an aldehyde, it's located on the first carbon, whereas in a ketone, it's somewhere in the middle of the chain. This leads to different chemical properties, which we would study later on in chemistry. At this stage, it's about recognizing the differences. Carboxylic acids and esters are said to be isomers of each other. Okay, you could have the same formula and produce either a carboxylic acid or an ester. Okay, we typically call this, lovingly the COO group, okay, COOH. We're going to be studying acids and bases at length, and these are very typical organic acids where they have this COOH group. So I'll just draw this one out to kind of show you again. So you've got C, so there's a carbon here and a carbon here, but then not a carbon in between here. So this is then attached to the OH, And then coming off of this, I have a double bond with the oxygen. Remembering that if we were to think about the oxygen, it actually has those 2 pairs of lone pairs for its octet. And then the carbon has the H's. Every carbon has 4 bonds. Every oxygen has 2 bonds. Okay? And then we've got our H. And I could have drawn this OH separately if I wanted to, like that. So it's a single bond to the O and then a single bond to the H. In an ester, what we have instead of a hydrogen here, we have another carbon group. So this at the end here, I've got a CO, and then instead of there being another H, I've got another organic chain or carbon chain coming off of that. The last 2 sets are amines and amides. These are some of our molecules that contain nitrogen. So amines have nitrogen and it's all single bonded. They're more closely related to, say, an alcohol that has OHs. And then an amide is more closely related to an ester. Instead of the oxygen here, we've got a nitrogen. And with nitrogen, nitrogen has 5 valence electrons, so it will always have 3 bonds. So here, although they're not shown, you can see this would have 2 hydrogens attached to ensure that it has the 3 bonds total. The last thing that we're going to do, just to show you an IR, just so that while you're doing your exploration during this lesson, you can see and be focused on what you actually need to be able to do. Okay? There's lots of information about IR, and if you're interested, there's lots of room for you to explore in more detail, but I just want to have you focus on the key ideas here. What we're going to be able to do at the end of this lesson is be able to look at an IR spectra and recognize that these peaks that we're seeing within the structure, within the spectrum itself, are going to give us information about this molecule. Okay, so when you look at this molecule, you can see it's called hexanoic acid. You don't need to name it, but you can see this is the key functional groups that you have. You have a carboxyl group, so you have a C double bonded to O and then an OH group. And then what you learn through your studies of IR is that an OH gives this very typical, very large peak. Okay? And then we have what's called the CO stretch, which is a very long finger at about this position in the IR spectrum. So I'll leave it there, but just so that you're focused and you know what you need to know, and to know that at the end of the day, what you're going to be able to do with this is very simplistic. You're just going to be linking your knowledge of functional groups to the different peaks that you see in the IR spectrum.